This is Math 154, Unit 6, and we're beginning this unit which covers the first 3 sections of your textbook in Chapter 9. Okay. The first thing I'd like to do is just kind of ask a couple of questions and remind you of a couple of things that you already know, and this is just kind of motivating what we're going to do in this chapter. The next couple things I'm going to show you are not in your notes. They're just, again, motivation for Chapter 9, so I would invite you to just kind of sit back and relax, just kind of absorb it. This isn't anything you necessarily need to write down. So I want to start with a question. Let's suppose that you were given this problem. Evaluate for x equals 1.5, and then the dreaded words, by hand. What I'd like to distinguish between is a time-consuming process and a really hard process. If the function is x to the 4th power, that would be a time-consuming process, right? When you plug in the 1.5 to the 4th, and you multiply 1.5 times itself 4 times. It's not hard, it's not difficult. You could do it, it's just going to take you a little bit of time. Now, I've done that behind the scenes because none of you really want to sit here and watch me multiply numbers, but you could certainly do that and you'd get 5.0625. So I'm thinking of this as time consuming, but not hard. Now consider the next problem. This time the function f of x is the natural log of x. So when I plug in my 1.5, I'm asking for the natural log of 1.5. This isn't a matter of something that I know how to do and it's just time consuming. This is a quote-unquote hard problem, right? In fact, it's not a problem that you probably would be able to do by hand at this stage. However, miraculously, our calculators always seem to be able to know, right? When we plug something like that in, our calculators seem to be able to almost instantaneously give us this marvelous answer. And the question that you might ask yourself is, how does the calculator know? I chose 1.5, but the calculator does it just fine, even if I choose 1.269742558, right? Some weird number. Calculator is still just fine, giving me an answer. Do we really believe that somebody tried all possible numbers, which isn't really possible, right? Because there's no such thing as all possible numbers. There's infinitely many numbers. And somehow programmed those into this calculator so that when I picked some random number, it would know the natural log? I don't think so. That's not reasonable. So what we're going to be doing in this section, and in fact in this chapter, is we're going to be investigating a method that does rely on series that will help us explain how the calculator can answer those hard problems that we really at this stage don't have any idea how to do by hand. All right, I'm going to start by asking you to remember something that you actually already know. It's something that we did in Calc 1 called linear approximation. I've got this problem all the way worked out. Again, it's not in your notes. You don't have to write this down. Just kind of sit back and absorb this for a moment. In Calc 1, we sometimes took functions like the function ln x that we were just looking at, and we did what was called a linear approximation at, for example, x equals 1, and we could use that to approximate the value of the natural log of 1.5. Now, linear approximation was just a fancy way of saying the tangent line, right? Because it's a linear function that approximates the function. And we know that if we stay close enough to x equals 1, like maybe 1.5, then the value of the function and the value on the tangent line are pretty close together, right? The closer I stay to 1, the better that approximation is going to be. So let's just go through a quick example to remind you how you found linear approximations, also known as the equation of the tangent line. In this case, I specifically wanted the linear approximation at x equal 1. So my x value is 1. I can get the y value just by plugging x equals 1 into my function. So the natural log of 1 is 0. And that's actually my point of tangency right here on the graph of y equals ln x, the point 1, 0. To get the slope of the tangent line, we use the derivative. And f prime, the derivative of ln x, is 1 over x. When I plug in my x equals 1, that just gives me a slope of 1. So I've got an x, a y, and an m. I'm going to take all of that information and plug it into the equation of a line, y equals mx plus b. And here that is. Y is 0. Both m and x are 1. And that allowed me to solve for the b value, negative 1. And so with a slope of 1 and a b of negative 1, there's the equation of my tangent line. Y equals 1x minus 1. And that's the equation of the linear approximation. Y equals x minus 1. What we did then was we said, okay, we're now saying that the natural log of x function can be approximated by this straight line, y equals x minus 1. So the natural log of x is approximately equal to x minus 1, again, close to the value of x equals 1. The closer we are to 1, the better that approximation is going to be. If I plug 1.5 in, what I'd be saying is that the natural log of 1.5 can be approximated by 1.5 minus 1. And so I'm saying the natural log of 1.5 is about 0.5. Now, if you actually do the natural log of 1.5 on your calculator, you're going to get 0.405, 465, etc., etc. So, am I close? Kind of, but I'm only within about a tenth. It's not great. Obviously, the calculator must have a better way. It must have a way to get a whole lot closer than I can get by a linear approximation. So here's the concept we're going to be working with in section 9.1. We're going to say, if we can do a linear approximation, could we also do a quadratic approximation? Could I approximate this not with the equation of a line, but with the equation of a parabola, and maybe do better? And of course, if there's a linear and a quadratic approximation, isn't there a cubic approximation? Or a fourth degree or fifth degree and so on? And the answer is yes, there are. Those higher order approximations are going to give us better and better estimates for the value of the natural log of 1.5, as we're going to see in this example that we're going to follow all the way through this section 9.1, or at least this video of it. Okay? So that's our goal, is to come up with higher order approximations that give better results than just the linear approximation. So with that background, we are ready to get started. As soon as I find what I do with my blank notes, I will pause and be right back. There we go. All right, so the notes begin then in section 9.1 with the title Taylor Polynomials. And it just sort of says, remember linear approximation. And of course, with that little review, we can now say, yes, we certainly do. What I'm going to do is I'm going to redo this idea of linear approximation in general without using a specific function or a specific x value. So the linear approximation is really just the equation of the tangent line. And so if I have some generic function y equals f of x, and my goal is to find the linear approximation, or in other words, the equation of the tangent line at some specific x value. Let's say that's x equals a in general. Then to find the equation of that tangent line, or linear approximation, I need the point and the slope to come up with the equation of a line. So my point would just be x equals a, and to get y, we'd just plug a into our function, so the y value here would be f of a. And the slope is always the derivative, so f prime, and we're going to plug that a value into f prime. And so we've got y equals mx plus b. Y is f of a. The slope is f prime of a times the x value, which is a, plus b. And so I would have b is f of a minus f prime of a times a. So y equals the slope, f prime of a, times x, plus b, which is f of a minus f prime of a times a. And I'm going to do just a little bit of algebra on that. I'm going to go ahead and I'm going to combine those two terms that have the f prime of a in them, and I'm going to factor out the f prime of a. So f prime of a times x minus a plus f of a. This is the form that I'd like to use for sort of the generic equation of a tangent line or linear approximation. All right, knowing where we're kind of going here, remember we talked about just a few minutes ago, the linear approximation only gives us so good an estimate, and we're interested in maybe there being a quadratic approximation or a cubic approximation. I'm going to kind of just use a slightly different notation here. Because this is a linear or a first degree approximation, I'm going to say this is called P1, the first degree approximation. And I'm going to rewrite it just slightly. I'm going to put the f of a term first. Other than that, everything else is going to stay the same. So again, notationally, a couple things to notice. It's first degree, so we label it P1. And then notice in the actual function, f of a is just a constant. Right? F prime of a is also a constant. It's just the derivative evaluated at a. So here's the first degree. We have x minus a to the first power. All right. I want to investigate a little bit more about this linear approximation and why it does a semi-okay job of approximating the original function. Right? So we're looking right now for how well the function itself agrees with a linear approximation at the value x equals a. So the value of f at x equals a, of course, is just f of a. Now if I plug x equals a into my approximation, I would get f of a plus f prime of a, and I'm substituting a for the x here, so times a minus a. Of course, since a minus a is 0, that whole term is going to go to 0, and I get f of a. These agree perfectly. Is that a surprise? Of course not. We know that the tangent line agrees perfectly with the function because it was the point of tangency where they have that perfect agreement. All right, let's next see how well the first derivative of the function matches with the first derivative of P1, again evaluated at x equals a. Well, the first derivative of the function, f prime, evaluated at a, is just f prime of a. No big deal. But let's look at P1 prime. P1 prime would be, now keep in mind, there's some constants in disguise here. F of a is just a number. It's the number you got by plugging a into the function. And the derivative of a constant is 0. Plus, again here, f prime of a is just a constant. It's the number you got by plugging a into f prime. But this time it's a constant multiplier, so I'm going to keep that f prime of a times the derivative of x minus a. The derivative of x is 1, minus the derivative of a is 0. So P1 prime of a is going to be, there's actually not even a place, there's no x's for me to plug the a into even. That's 0, that's 1, so I'm going to get f prime of a. And again, these guys agree completely. Perfect. Once again, not a real surprise. Because it was the tangent line, we wanted it to just skim, or in other words, be going in the same direction, have the same slope as the function at that point. Now let's take a look at what happens when we get to the second derivative. The second derivative of f double prime, evaluated at a. If I take a look at my first derivative, right, even before I supposedly plugged in a, this just simplified to the constant, f prime of a. And the derivative of a constant is 0. So, my function and my approximation P1 do not agree at the level of the second derivative. Again, not a surprise. This was a linear approximation, and the second derivative of a linear function is always 0. So there was no way I was going to get agreement there. This, however, this idea of making the function and the approximation agree for various derivatives is what's going to allow us to build our quadratic approximation, our cubic approximation, and so forth. So, next page. What we just discovered was that P1 does agree with f of x on both the actual value and the first derivative. We are now going to say, let's find higher order approximations for f of x by requiring agreement at higher order derivatives. So if I were to think about P2, which is going to be our second order or quadratic approximation, we're going to go ahead and require that it agrees with f of x on not only the actual value in the first derivative, but that it also agrees with the original function at the level of the second derivative. Let's talk about the form that P2 would have to take. We're going to build on what we already know. P2 is going to start with these same two first terms. That's great because those already agree at the function level and at the first derivative level. So we're going to start with f of a plus f prime of a times x minus a to the first power. I now need to add a new term that's going to make it quadratic. Right? Well, if it's going to be quadratic, this had an x minus a to the first, so it would make sense that this one should have an x minus a to the second in it. That's what would make it second degree, second order, or quadratic. But what I don't know is what multiplier I should put here. This one had the multiplier f prime of a, but we need to figure out what multiplier to put on this term in order to get agreement at that second derivative level. So for right now, I'm just going to call it c, and our job is going to be to figure out what c is. All right, so I'm going to make another little chart, kind of like the one we had on the previous page. We're going to look for the value at x equal a. For f, and then for P2. So, for the function itself, if I plug in x equals a, of course I'm just going to get f of a. If I plug in x equals a to P2, I'm going to get f of a plus f prime of a times a minus a, plugging in x equals a, plus c times a minus a squared. And fortunately for us, since a minus a is 0, both of those terms become 0, and we just get f of a. So the function value and the P2 value agree at the function level. All right, what about the first derivative level? The first derivative of f would just be f prime, and we got to plug a in. The first derivative of P2, the derivative of this constant, f of a, is 0, plus, here f prime of a is a constant multiplier, and then the derivative of x minus a would just be 1, plus c is a constant multiplier, and then the derivative of this square would be 2 times x minus a to the first. If I now plug in x equals a, I have 0 plus f prime of a plus 2c times a minus a. Here again, a minus a is 0. So that's going to leave me just f prime of a. And we're good. We have agreement at the level of the first derivative. All right, here's the key. This is the new part, right? We now want to force this to have agreement at the level of the second derivative, which would be f double prime of a. So what I'm going to do is I'm going to look here at, this was really my first derivative right here, right? If I take another derivative of that, the derivative of this constant would be 0, plus the derivative of this term would be 2c times 1 minus 0. And that's going to give me just 2c. Now, I'm trying to figure out what c is. And I want the second derivative to not only exist, I want them to agree. So to make these agree, f double prime of a has to equal 2c, and p, f double prime of a over 2 is equal to c. So at this stage, I can now say I know what c is. C turned out to be f double prime of a over 2. And that's P2. All right, I know this is a bit time consuming, but I want to do one more and then I think we're going to be able to see a pattern. Okay? So if we can have a second order or quadratic approximation, we can also have a third order or cubic approximation. So P3, this is going to be third order, cubic approximation. I'm going to start out by saying we're not going to throw out what we already know. Let's start with all of this because we know this already agrees at the level of the function, the first and second derivatives. That's what we just did here. So let's start with all of this, but we're going to now add another term that has a third power. So I'm going to write P3 as everything I've got so far. But now I'm going to have a new term that would have a third power, x minus a cubed in it. And again, I don't know yet what that multiplier will be. I'm going to choose that multiplier to force it to agree with the function at the level of the third derivative. So for right now, I'm just going to call it c. All right, one more time. The value at x equal a the function itself, and then P3. The actual function will, of course, just be f of a. And notice that if you plug x equal a into our P3, you're going to get f of a. Plug x equals a in here, and this term will become 0. Plug x equals a in here, and the quadratic term becomes 0. And plug x equals a in here, and the cubic term becomes 0. So it all simplifies to f of a, and we're good to go. They agree. First derivative is going to be f prime of a. If I take the first derivative of this function, P3, the derivative of a constant is 0, plus f prime of a is a constant multiplier, and the derivative of x is 1, plus that's a constant multiplier. So when I take the derivative, the 2 is going to come down and cancel, and I'll just get f double prime of a times x minus a to the first. Plus, the derivative of this term will bring the 3 down, so we'll have 3c times x minus a squared. That's my first derivative. which we'll use in a couple of minutes to get the second and third derivatives. But just note again that if you were to plug in x equals a, you'd have 0 plus f prime of a times 1 is f prime of a. Plugging in x equals a here is going to make that term all become 0. And plugging in x equals a there gives 0 there as well. So this does simplify to f prime of a, and we have that agreement again. All right, hang in there. Second derivative. For the function, of course, is just going to be f prime of a. All right, this was my first derivative. So for p, I'm going to use this to get to my second derivative. So I already had 0. That's a constant. There are no x's there, so the derivative is 0. Here we have an x, so I've got my f double prime of a as the constant multiplier, times the derivative of x minus a, which is 1, plus the derivative here. We'll bring the 2 down, so that becomes 6c times x minus a to the first. So that's my second derivative. I'll go back to that in a couple minutes when I'm ready to get the third. And if I plug in x equals a, I have 0 plus 0 plus f double prime of a. And when I plug x equals a in here, that becomes 0. And all of that just equals f double prime of a, and we get agreement at the level of the second derivative. None of that is surprising. We had already gotten the function designed that far, right? All right, here finally is the new piece. I now want to require that these things agree at the level of the third derivative. So the third derivative is going to be f triple prime at a. And I now want the third derivative of p3. Again, just a reminder, this was the second derivative right here. So I'm going to take the derivative of this to calculate the third derivative of p3. I have 0 plus 0. The derivative of this constant term is 0. And the derivative here, this does have an x, so we just have 6c as a constant multiplier times 1, which all equals 6c. I want to force these to agree. So, to make them agree, it must be true that the third derivative evaluated at a is equal to 6c, and c is going to be f triple prime of a over 6. And that's this a value, or c value rather, that I needed to make p3. All right, so as you can see, this is a bit of a pain in the neck. It's a bit of a time-consuming process, so we'd rather not keep on doing this to get a 4th degree, 5th degree, 6th degree. Instead, let's see if we can recognize some patterns. First of all, I will certainly notice that in terms of my x's, the x minus a just goes from the first to the second to the third power. That's no problem. That's an easy pattern. And the f primes themselves also follow the pattern, right? The 0th derivative, first, second, and third derivatives. So that's an easy pattern. What I'd like to concentrate on for the moment is those denominators. This one would really technically have a denominator of 1, and so would that. So take a look at those denominators. I know it's early days in this game yet, but do you think you might see what those values are? Do they look like factorials to you? 0 factorial by definition is 1. That's 1 factorial. That's 2 factorial. That's 3 factorial. In fact, that's exactly what they are. And if you think about it, where this comes from is actually just the power rule for derivatives, right? Right here, when I brought that 2 down, we got 3 times 2 times 1 was 6. The next time we would have had a third power to bring down, and then a fourth power to bring down, and so on. So we're going to continue to bring down one higher number every time, and that's going to create those factorials in the denominator. So I think we have enough of a pattern to write down a general description. If we define P sub n as the polynomial that has to agree with f of x on the actual value and all of the first n derivatives, we can now say, based on our pattern, P sub n should equal, I'm going to write this as a series. Grab this again. And let me look at sort of a generic term like this one. First of all, if we take k going from 0 to infinity, this is going to be the kth derivative. This would be the k equal 3 term, right? So that would be the kth derivative evaluated at a. The denominator is the factorial over k factorial times x minus a to the k power. Right? That works all the way back. Here's the second derivative over 2 factorial to the second power. There's the first derivative over 1 factorial to the first power. And this one technically would be the 0th derivative, f of a, over 0 factorial. And the 0th power of this is just 1, which is why we don't see it. So if we were to sum up all of those terms, we would get this big sum. So there is my formula for P sub n in general, and we can go out as far as we need to. And you know what? I jumped the gun a little bit. If I want only the P sub n, I really don't want to go to infinity yet. I want to stop when I get to the nth term. So if I do stop when I get to the nth term, what I have is called the nth order Taylor polynomial for f, centered at x equal a. Right? All right, what's amazing about this? I know it might seem like we've done a lot of work and you're like, well, what have we got here? Let me go back to my introduction. Remember this? Oops, not that. I don't know what I did with my introduction. Here it is. What's easy, although maybe time-consuming to evaluate, and what's hard? Polynomials, although maybe time-consuming, are not hard to evaluate, right? Things like natural logs, or exponentials, or trig functions, those are hard problems to do by hand. Notice what we've done here. We've now said that for any function f, an exponential, a trig function, a log, we can turn that function into something that's a polynomial, right? This is just a big, long polynomial, powers of x. Polynomials are maybe time-consuming, but aren't difficult to evaluate. So that's what we've accomplished with this Taylor polynomial. We've said that we can take any function, no matter what it is, and approximate it using a polynomial function. As you can imagine, in the days before fancy calculation devices, this is huge, right? Because days before fancy calculation, this would have been the way that someone would have had to have used to actually approximate the value, for example, of the natural log of 1.5. And we're going to go back to that example right now. So this is my big takeaway. This is a formula that we've now kind of seen where it comes from, and we're going to use that as the formula for our Taylor polynomials. All right. My first example, I'm going to go back to the one that we kind of previewed with, the idea of the natural log. And we're going to say, let's look at f of x being the natural log of x. And I would like to center this at x equal 1. Right? So I'm basically redoing the same problem that we used in the preview. F of x equals ln x. The approximation at the value x equals 1. We had already done the linear one and saw that we weren't all that close. My goal now is to say, let's now, with our newfound formula, see if we can get a quadratic approximation, a cubic approximation, a fourth degree approximation, and see how much better we can do at actually approximating the natural log of 1.5. So here we go. For f of x equals ln x, centered at x equal 1, I would like to find the approximations p0 through p4. What I always like to do before I start these problems is I know I'm going to continue to need derivatives, right? I'm going to need the first derivative and then the second derivative and the third derivative and so on. So I like to start by just kind of off to the side, making myself a little table of those derivatives, and that allows me to quickly grab them when I need them. So let's see here. We'll find each derivative, and then we'll evaluate it at our x value, which is x equal 1. And I'm going to put n here. So the 0th derivative is the function itself, ln x. And if you plug in 1, of course ln 1 is going to be 0. The first derivative would be 1 over x. And if I plug in 1, I get 1 for that value. We're going to need to go all the way up to the 4th term, so I'm going to go through the 4th derivative here. Second derivative, that would be x to the minus 1, so minus x to the minus 2, or negative 1 over x squared. Negative 1 over 1 squared gives me negative 1. Third derivative, that's minus x to the minus 2. So that would be positive 2x to the minus 3. Oops, positive 2x to the minus 3 is x cubed on the bottom. Plugging in 1 gives me 2. And one more. The 4th derivative, derivative of 2x to the minus 3rd, would be negative 6x to the minus 4th, or negative 6 over x to the 4th. And plugging in 1 gives me negative 6. Okay. So therefore, n equals 0 through 4 are just my derivatives, which I'll be able to use to plug in for my Taylor polynomials. So that's kind of an off to the side. All right, so let's get started. P0. If I just think of the 0 term, right, that would be the 0th derivative, or just f of, in our case, 1, over 0 factorial, times x minus our a value is 1, to the 0 power, right? This is just my k equals 0. By the way, I probably should have mentioned this before. When we say centered at x equal 1, that's really giving us the a value. A is 1. All right, well, let's see here. That one's not too tough. F of 1, our 0th derivative was 0. And 0 times anything is 0. So P0 is just 0. All right, let's go to P1. Now the nice thing about these things is they build on each other. So P1 is going to be what we had before, which was 0, plus I'll add on a k equal 1. So when I do k equal 1, I have the first derivative, which I have over here in my chart, is just 1, over 1 factorial times x minus RA is 1 to the first. 1 factorial is just 1, so I'm just going to get x minus 1. Okay. Let's keep going. I'm going to go down here because I'm going to need a little more space. P2. So again, I always keep what I already had. I already did the k equals 0 and the k equal 1 terms. So I keep them. And then I add on my new term. The top, again, was now the second derivative. My second derivative is negative 1 over k factorial, so 2 factorial, times x minus a, which is 1, to the second power. So I have x minus 1 minus 1/2, since 2 factorial is just 2, times x minus 1 squared. Just to help us see the pattern a little bit better, I'm going to group those together and call them x minus 1 to the first so we can really see that polynomial developing. All right, P3. Once again, we start with what we already had. Just build on it. So I'm now going to add on the k equal 3 term. The numerator is my third derivative, which is 2. The denominator, k factorial, 3 factorial, times x minus 1 to the third. So I've got x minus 1 to the first, minus 1/2, x minus 1 squared. That would be 2/6, which I can simplify to 1/3, right? So plus 1/3, x minus 1 cubed. And there's my P3. All right, we got to do one more. P4. That sound like a broken record, but here we go. We got to keep what we already had. And now I have to add on the k equal 4 term. So plus, the numerator is the fourth derivative, which is negative 6. The denominator will be 4 factorial times x minus 1 to the fourth. And let's see, what's this thing? That would be negative 6 over 4 factorial is 24. So that'd be negative 1/4. All right, so there's the first, technically 5 Taylor polynomials, including the P0. And each one of these should be giving us a better and better approximation for our natural log function. What's really kind of cool at this stage is that oftentimes, not every time, but oftentimes, when you start looking at these, you can start seeing a real pattern, and you can say, hey, I think I could actually write that as a series. In this case, I believe we can. If I think of this first one as 1 over 1, did you notice that in the constants, the multipliers, the numerator is always 1, and the denominator is just the k value, right? 1, 2, 3, 4. With the first, second, third, and fourth powers. But notice also that this series is going to alternate. Positive, negative, positive, negative. So I think we can probably make a pretty educated guess at what Pn is going to look like. if I want to try to write a series that represents Pn, I'm going to take the sum. And technically we always start from 0 on these, but because my K0 term here was just 0, I'll start at 1. So from 1 to n. And each term is going to be 1 over n, right, like this is the third term. I'm sorry, 1 over k, my fault, n is the final number. So if I just look at this one for a k of 3, I'd have 1 over k times x minus 1 to the k power. And then I have to make it alternate. So that would be negative 1. I'm going to start with the k power, and then I'm going to ask myself if that works or not. If I do that, when k is 1, my first term would be negative. And when k is 2, my second term would be positive. That's exactly backwards from what I want. So I can fix that easily enough by just making that exponent of k plus 1. Right? Sorry, that got a little crunched. Let me write it one more time. And in fact, I'll simplify just slightly. I'm going to put that negative 1 to the k plus 1 in the numerator. Over k times x minus 1 to the k. So once I've seen the pattern, it means that if I wanted P5, P6, P7, I wouldn't necessarily have to go all the way back to the Taylor polynomial definition. I could actually just continue the pattern that I'm seeing here. All right, part C asks us to graph, and I'm going to ask you to hold off on that just for a couple of minutes. We're going to come back to that. I'm actually going to pull out Desmos, and we're going to do that. But before we do, I want to do the numerical evaluation on the next page. So we'll come back to our graph in just a few minutes. What I'd like to do first is I'd like to approximate the natural log of 1.5 using our Taylor polynomials. And the question that I'm asking us is what degree Taylor polynomial is going to be required in order to get our approximation accurate to 3 decimal places. Right? Just a reminder, on the calculator, the natural log of 1.5 we know to be, on the calculator, 0.405, 465, etc., etc., etc. So I'm now going to go ahead and start experimenting with these Taylor polynomials to see when do I get that third decimal place to be accurate. How far do I have to go? Okay. So here we go. I'm going to start writing out Pn, and I'm going to use our little pattern here. Let me put that up. We already know from here, right, that we started out with just x minus 1 to the first. And then we had that minus 1/2, x minus 1 squared, plus a third, x minus 1 cubed, minus a fourth, x minus 1 to the fourth. And just based on this pattern that we figured out, as well as the pattern that we can see here, if I were to continue this, my next term would be positive, and then a fifth, x minus 1 to the fifth, and my next term would be negative, a sixth, x minus 1 to the sixth, and so on. Right? I could easily go as far as I needed to now that I have the pattern established. So, for each value of n, I'm going to make a little table here, and I'm going to find P sub n of 1.5. We want to figure out what n value will the polynomial evaluated at 1.5 agree with the actual value out to 3 decimal places. P0 in this case was just 0. That doesn't agree at all. P1, here's P1, right, out that far. And I'm just going to grab my calculator and do this as we go along. So for P1, I'd be plugging 1.5 in here. Obviously 1.5 minus 1 gives us our old linear approximation of 0.5. P2. We've got to go out to here to get P2. So I'm going to take the P1 that I already had, and I'm just going to add on this next term. So in my calculator, I already have the 0.5. I'm going to subtract that answer, there we go. Subtract 1/2 times 1.5 for x, so 1.5 minus 1 squared. And I get 0.375. Okay, let's keep going. For P3, I would have to go all the way out to here. So when n is 3, I have the 0.375 already. And then I'm going to add 1/3 times 1.5 minus 1 cubed. And I'll keep about 5 decimal places here. 0.41667 if I round to 5 decimal places. All right, n equals 4. I got to go out to here. So everything I already had. And now this time I'm subtracting 1/4 times 1.5 minus 1 to the 4th power. 0.40104. All right, we're getting close. Notice what we've got here. We've got the first 2 decimal places accurate right now, but I wanted 3, so I'm going to keep going. All right, P5. Again, I take what I already had, and this time I'm adding 1/5 times 1.5 minus 1 to the 5th power. 0.40729. Let's try 6. We're not there yet, right? We don't have that 3rd decimal place. For the 6th one, I'm going to add on this term. So I take what I already had. I subtract 1/6 times 1.5 minus 1 to the 6th power. If I rounded, I'd have it, but I don't technically have it yet. 0.40469. All right, looks like I'm going to have to go probably just one more. I didn't write it up here, but the next one would have been a plus 1/7. X minus 1 to the 7th. So we take what we've got. We add 1/7 times 1.5 minus 7, minus 1 to the 7th power. There it is, 0.40580. Now if I rounded, of course it would round up, but all I asked for was accuracy in the first 3 decimal places, and we now have it. So we would have to go out to the 7th degree in order to get 3 decimal places worth of accuracy. All right, now you might think, holy cow, is that really what the calculator does? I'm not going to claim that we're quite there yet, but yes, indeed, these infinite series, because this would go on forever, are really what the calculator is using. These are the processes that are built into our calculation devices. Of course, the difference between us doing this and the calculator doing this is for us to make all of these calculations and plug everything in is taking time. But as you know, calculators and computers work far faster than we do by hand. And so they're just doing many, many more of these and going out much further than we can do manually in a big hurry. Right? But ultimately, what I really want you to notice is yes, every single time we use a higher degree or a higher order Taylor polynomial, we did get closer and closer and closer and closer to the actual value of the natural log of 1.5. All right. I know this is kind of going on, and I apologize for that, but I want to do one last thing. I wanted to go back to this whole idea graphically. And that's going to be, if you want to jot anything down, you can actually use the graph on the bottom of page 4 here. But I'm going to switch over, and I'm going to take a look at this on Desmos. So give me a second to make that change. Here we go. So here you see a Desmos screen, and you'll notice that I've already got y equals ln x graphed. I've got a relatively small window here from, I think, just like -1 to +1 or something like that, and then from -2 to 2 on the y-axis. But this is that graph y equals ln x. Okay. Here, I've got the first linear approximation graph. That was my P1, which was x minus 1. And not surprising, right? We kind of know how to do that even in Calc 1. I'm also going to go ahead and just this dotted line represents x equals 1.5. So you can kind of see there's the actual value of ln x, 0.405 up to 3 decimal places. And there it is on the, there it is, sorry. There it is on the linear approximation. 1.5, 0.5. Right. Let me get rid of all those. I did that one twice. Come on, there we go. All right, let's go ahead, and I'm now going to include the quadratic approximation, which I've already got typed in here as P2. There it is. It's this kind of purplish curve. And you can see that right here at 1.5, do you see how much closer the purple curve is to our natural log graph as compared to the line? The quadratic approximation is definitely better. There it is. There's that 0.375 that we got in our chart if you look at it. Let's take in another one. Let's put in p cubed. P cubed is this blue line. You can barely see how it's different from the original function. There's the y value, the 0.417. We had 0.41666, right? And you can see that it is really, really close to our original red graph of ln x. We did one more, P4. This is this orange graph here. And there's the 0.401 that we got for P4. Those are the only ones that we did on the page that we were doing this. I didn't type any more in. So you can see how the approximations get better, how the graphs get closer and closer to the natural log graph. I'm going to take out this 1.5 now. Notice that not only at 1.5 do they get closer, but the graphs stay closer to the natural log curve for a longer period of time, right? I'm going to go back one more time. Here's P1. And notice that you can easily already see that it's splitting apart here by the time we get to maybe the second little bar, second spacing. Here's P2. And notice that out here, you can see how the line has split way apart. But out to here, the quadratic is staying pretty close. I'm going to get rid of P1 and I'm going to go to P3. P3, the blue graph, stays closer than the quadratic all the way out to about the third spacing here. And now if I look at P3 and P4, They're almost hard to tell apart, right? The original curve, the red one, and the orange one are almost the same all the way out here to the third and even really close out here at the fourth spacing. So you can see that not only are they closer, but they stay closer longer. These polynomials are actually trying to approximate the graph of the original natural log curve. All right, I'm going to stop there because this is a really long video, and we're going to look at some other examples besides ln x in the second part of section 9.1, the next video.